This is an infrared remote controller. Here's another example, another, and another. Beside these, we can find a lot more remote controllers in the market and around us. Many people think that these remote controllers are specific to their devices and can't be used anywhere else. But in this video, you will see that you can use all of these remote controllers in your projects. You will also learn the hardware level theory behind these remote controllers as well as the practical tips on using them. After watching this video, you will be able to use many type of infrared remote controllers in your projects. That's a cool skill, right? So watch the video carefully until the end. On any type of infrared remote controllers, there is one of these infrared transmitters, and on the receiver, one of these infrared receivers is used. If you look closely, you can see that in front of all the remote controllers, there is one of these infrared transmitters. Of course, I believe that a suitable name has not been chosen for this component, because when we say infrared transmitter, it creates the impression in the listener that this component probably has a magical property, while this is not the case. This component is just a simple LED that produces infrared light instead of visible light. You must know that infrared light is not visible to the naked eye, but in a video camera, almost any type of digital camera, you can see it. That's why in security cameras, infrared LEDs are used next to camera to produce infrared light, invisible infrared light, and in this way gives the camera night vision capability. That is, it does not produce light for human vision, but it creates night vision capability for the camera. If you hold these remote controllers in front of your mobile phone camera and press one of its buttons, you will see that the remote control is sending something, and this is quite clear in the camera. Look. It seems that the transmitter is sending signals, but the matter is not that simple. We need to think more about it. When we press one of the buttons on these remote controllers, the 4-byte code specific to that button is sent by the remote controller. This 4-byte code includes 2 bytes of remote controller address and 2 bytes of command. That is, each company chooses a unique address for itself so that its remote control does not interfere with the remote controller of other companies. For example, the Philips remote controller does not work on Samsung products. The difference in device address is so that the remote controller of different devices do not interfere with other devices and do not control them. Imagine if it were like this. When you want to turn off the fan, your TV would also turn off. Imagine how bad it would be, especially if you are waiting for your favorite team to take a penalty at that moment and miss the penalty scene. It would be a disaster, really. On the other hand, for each button, each company selects a unique code as the command code so that that button performs the same function on all its products. For example, if it wants the power button of the remote controller of one of its products to be able to turn off or turn on other products of the same company, it selects the same command code for the power button on all its products. Now, in this video, we don't want to enter into commercial and non-technical discussions, and we consider the same simple definition. That is, we say that each button sends its own unique 4-byte code. Each byte was equivalent to 8 bits. So these remote controllers sends unique 32 bits of information by pressing each button, and the receiving device, by observing each unique 32-bit code, performs a specific action based on the program that we have programmed and defined for it. You must know that each bit can be a logical 1 or logical 0. In fact, the transmitter sends a 32-bit string of combination of zeros and ones. If it seems simple so far, I have bad news for you, because it is not that simple and there are many points here. For example, how each of these bits is sent. You might think that when the remote controller wants to send a logical 1, it turns on the transmitter, and when it wants to send a logical 0, it turns off the transmitter. Of course, this is one of the most simplest scenarios we can imagine, and it certainly works in a laboratory condition, but in a real condition, I don't think it will work because we have many sources of infrared light in the real environment. The sun, heaters, ordinary lamps, and even the human and animal bodies produce infrared light, and all of these are received by the receiving device, which makes it impossible for us to understand in the receiver circuit whether this received light was sent from the desired transmitter or received from the environment. For example, the receiver circuit might have trouble distinguishing between infrared light emitted by a person nearby and light from the remote controller. So we have to think of a solution so that the receiver can always distinguish the light received from the remote controller and the natural lights of the environment so that it can always work correctly. For this purpose, we need to use the carrier frequency. You might wonder what the carrier frequency is. Good question. Let me give you a simple example. Suppose that you are standing somewhere on a dark night and someone is going to signal you from a distance with a light, and there are many other light sources around. For example, the lights of houses are on, the street lights are on, and the cars around you have their lights on. If the person signaling is supposed to signal you by turning on a light, can you tell which of these light sources belongs to that person you want? I don't think so. But if you have already coordinated with that person to turn the light on and off with a special rhythm, for example, twice per second, then you can better distinguish that person from the rest of the light sources. When you see a light turning on and off at a frequency of 2 Hz, that is twice per second, you realize that the person you want is sending information or signaling. We use exactly the same technique to separate the infrared remote controller from other natural light sources that are always present in the environment. So, we make an agreement between the transmitter and the receiver that instead of showing the logical level 1 by simply turning on the infrared, the transmitter should show it like this by turning the infrared light on and off at high speed and showing the logical level 0 by completely turning off the transmitter. In this way, we can understand whether the transmitter is sending something or the signal we receive belongs to the surrounding environment. This is the stage where we can easily send logical level 1 and logical level 0 using infrared waves. But what I said is only logical level 0 and 1, and it is different from those bits of code that are related to the remote controller's keys. That is, with this technique we can send a waveform like this, and the receiver receives this waveform, but it must interpret it itself what information was sent by the transmitter, which also has its own special points, which I will explain it later in this video. But before that, there are a few points I need to mention about sending this waveform. The first point is the carrier frequency. Here, here, and here. The speed of turning the transmitter on and off to send the logical level 1 here, here, and here. In fact, we can use almost any frequency, but now the standard frequency is 38 kilohertz, which means that many of the remote controllers and receivers that you see around you use 38 kilohertz frequency to send and receive information. That is, the transmitter generates an infrared signal with a frequency of 38 kilohertz to send the logical level 1, and to send the logical level 0, it completely turns off the transmitter, meaning it doesn't send anything. For better understanding, we can easily test it with a simple experiment. For this purpose, I'll connect an infrared receiver in series with a 1 kilo ohm resistor, and I'll connect the power supply. Then, by probing the connection point of the two parts with an oscilloscope, I'll see the waveform sent by the transmitter. Look here carefully at this waveform. These parts are logical zeros and these three parts are logical 1. If we zoom in on the logical level 1 here or here or here, we will see that there is an alternative wave with a frequency of approximately 38 kHz here. Look here, 37.9 kHz is written here, which is almost equal to 38 kHz. The number 38 kHz is a convention that everyone has accepted. On the receiver side, we have to receive the signal in the environment, extract the 38 kHz signal from it, and determine when the 38 kHz signal is in the environment and when the 38 kHz signal is not in the environment, so that we can receive the waveform sent by the transmitter. But this is not an easy task and requires a lot of skill, expertise, and knowledge in the fields of designing amplifier circuits, filtering, and signal processing. But if you don't have this knowledge, there is no need to worry, because there is a simple solution. Several manufacturers have already discovered this need and have introduced a completely ready and independent component to the market that does just that. That is, it detects the presence of a 38 kHz signal in the environment and based on that, delivers the appropriate logical levels in its output pin very simply and neatly. I mean these 3-pin infrared receivers. These 3-pin infrared receivers have different names and shapes. For example, this one has the part number HS0038, which does exactly the same thing for us. This IC has 3 pins, 2 of which are related to the 5-volt power supply, and the third pin is the output pin. Just connect the 5-volt and 0 volts to the VCC and ground, then the IC will start working and will deliver the output signal to us in the output terminal here. In fact, inside this component there is a 2-pin infrared receiver like this one, the simple component, along with filtering and amplifier circuits, etc. But I'm not concerned with the internal details of this IC. I just use it. I'm gonna test it. I have set up this simple circuit to test this IC. That is, I have connected the VCC and ground of this IC to the power supply and connect the output pin to the VCC with an LED and a resistor. You can see that when I press the remote controller buttons, this LED turns on and off in the IC output. We saw that when we press the remote button, something happens in the receiver's output, but nothing is clear from this turning on and off of the LED. But if we see the signal on the receiver's output pin on the oscilloscope, we may be able to get more information. For example, if it has a specific waveform. I think it's a good idea to test it. If I connect the oscilloscope, we can see that by pressing each button, the waveform corresponding to that button is displayed on the oscilloscope screen. For example, when I press the OK button on the remote controller, the waveform corresponding to that button can be seen on the oscilloscope screen. You can see that how clean and excellent the output of this IC is, and it is not at all comparable to what we received before with a 2-pin receiver. It is also interesting that the output of this IC is digital, and here there is no sign of a signal with a frequency of 38 kHz, and there are only clean logical level 0 and logical level 1 without any noise. Now the only thing we have to do is to interpret this waveform using a microcontroller and obtain the logical bits and as a result the 4 bytes related to the button code. After obtaining 4-byte code, we can decide what action should be done in the receiver circuit by receiving each 4-byte code. For example, in the 10-channel lighting system with an infrared remote controller, each of these number buttons was used to change the status of each of the channels. That is, the microcontroller, by receiving the code related to each of the numbers, decides to change the status of the channel related to that number. For example, if we press the number 4, the status of channel number 4 changes. That is, if it is on, it turns off, and if it is off, it turns on. By the way, I forgot to say that this video that you are watching now is the second part of the 10-channel flicker-free lighting system project with an infrared remote controller, which we did it with STM32 microcontroller. In this project, we designed the system to control 10 LED strips independently of each other, and also the system supports 10 different programs. Anyway, let's get back to the main topic. At this stage, the only missing link we have is the waveform interpretation, which I will teach you how to interpret this waveform and extract 4 bytes codes related to the button from the waveform. This is the waveform that the button sends. First, it sends a positive voltage with a duration of 9 milliseconds, and then it sends a negative voltage with a duration of 4.5 milliseconds. This means that a button on the remote controller has been sent, and then 32 bits are going to be sent. That is, after receiving these two voltages, we must wait to receive 32 bits of information. For each bit, a positive voltage with a duration of a half millisecond, and then a negative voltage with a duration depending on the value of the bit, a half millisecond or a short pulse, or 1.5 millisecond or long pulse is sent. That is, if the transmitter wants to send bit 0, it sends a positive voltage with duration of a half millisecond or a short pulse, and then a negative voltage again with a duration of a half millisecond. But if it wants to send the bit 1, it sends a positive voltage with a duration of a half millisecond or short pulse, then a negative voltage with a duration of 1.5 millisecond or a long pulse. In fact, the positive voltage here means the entry of a bit, and the width of the negative voltage determines the value of the bit. By the way, before I forget, let me also say that the values of half and 1.5 millisecond pulses that I already mentioned are rounded values. In fact, the width of the short pulse is actually 0.5625 milliseconds, and the width of the long pulse is actually 1.6875 milliseconds, and I rounded the values for the simplicity of my explanations. Let's get back to our discussion. I said before that by pressing a button, a total of 32 bits of data are sent, right? If we separate the bytes by a length of 8 bits, we see that 4 bytes of information are sent. The first 2 bytes are the address bytes that specify the device, right? For example, Samsung has assigned a specific address to its TVs. For this company's TVs, specific bytes are sent in the low value address and high value addresses. The value of the address bytes, as we know, is different for different companies and different devices. The next 2 bytes are the command bytes that specify the command, that is, the function of the key. Also, keep in mind that the LSB or low value bit is sent before the MSB or high value bit for each byte. That is, if you pay more attention, after sending 9 millisecond and 4.5 millisecond pulses, the LSB of the low value address is sent and goes in order until it reaches the MSB of the low value address, and after that, the LSB of high value address is sent until it reaches the MSB of the high value address. In the same way, the LSB of the low value byte of the command is sent until the MSB of the low value byte of the command, and after that, the LSB of the high value byte of the command is sent until it reaches the MSB of the high value byte of the command. After sending 32 bits of data, the transmitter sends a positive pulse with a duration of a half millisecond to specify the end of the message, and that's it. In this way, the code bits related to each of the buttons of the remote controller can be interpreted and identified. Regardless of the values of the address and the command, you can suppose that each of these buttons has a unique 4-byte values, and by receiving each of these 4-byte codes, you can start a process in the microcontroller. Exactly the same thing that we did in the lighting system project with an infrared remote controller. The last point is that this waveform that infrared remote controller sends is generally known as the NEC Infrared Communication Protocol, and you can independently search and research about it. Well, my friend, this video ends here. You've watched the second part of the project of the lighting system with an infrared remote controller. In the next part of the series, we are going to talk about the switching system in the output of each channel. Wait for the next parts of this project to fully understand the project details. Be sure to like this video, subscribe to my channel, and hit the notification bell so that when I release the next part, you will be the first one to come and see the video. By the way, all the files necessary for making this project, including PCB, schematics, and codes, can be received in the description section of the last part of this project. Until the next video, take care and have a good one.